degrees of freedom fairly quickly. So here's a quick rundown of what it is that we end up estimating if we have P-level covariance, P-level 1 covariance, Q-level 2 covariance, and a fully specified hierarchical linear model. That means Z affects every random effect. There are cross-level interactions. Then you would have fixed effects, the number that's equal to P plus 1 times P plus 1. That's the number of fixed effects you would be estimating. You would have to estimate one level one variance component. And then, if you want to have a fully structured matrix of variances and covariances between slopes and intercepts, you would end up estimating a half times P plus 1 times P plus 2 variance and covariance components. Now that quickly becomes a very large number. Here's sort of an example, not quite there. Here's what is required for the identification. Identification of the effects of the level 1 covariance, including the cross-level interactions, is fundamentally a function of the number of level 1 units. Usually we don't have a shortage of those. Mind you, it's not a function of the number of level 1 units in a particular cluster. It's every one over all clusters. There we usually don't have a problem, but when we get to the effects of the level 2 covariance, and when we get to the variance and covariance components of the level 2 errors, there the critical quantity is the number of contexts, J. We can essentially not estimate more effects than we have level 2 units. And to just give you a flavor of how quickly this can go awry, this is the 2009 European election survey where we have 27 countries and up to 27,000 observations at the level 1, say, individuals. So there's practically no limitation on level 1 covariance, but only up to 26 level 2 covariance can be included in the model. And then we've depleted all of the degrees of freedom. And up to 27 level 2 variance and covariance components can be specified. It means that you can really only specify random effects for about 5 predictors plus an intercept. Then we run out of degrees of freedom. This is a huge implication. And the implication is that it is usually not possible to take an empiricist approach to figuring out what is random and what is not. You cannot say, well, here is a level 1 model with 10 predictors, and I don't know which of these have random effects and which of them don't. I'm just going to specify everything as random and then just let the data tell me which of them really are and which of them are not, because we run out of degrees of freedom very quickly. So, in this sense, there is a big demand on theory. You sort of have to have an idea ahead of time what it is that should be allowed to vary and what it is that that should be constrained as fixed. And this is, I think, one of the bigger points that I want to make. Sort of will be a bit in the background, given that we will focus on all the technical ideas of multi-level analysis. But one of the points I want to bring up is that there are these theoretical demands, and that very frequently you have to know ahead of time to how to specify the model. But a little bit of background, because this is for us, it's important technology. basically, these models were developed in educational statistics for the most part. And the intriguing thing is that there is actually a fairly big difference between the sampling designs used in educational research and the ones that we tend to run into in electoral research and public opinion research. What they do in educational research is say they're quite interested in the effects of class size on students' performance. That's sort of a classical question in the literature. So they have these data sets where they sample literally hundreds of classrooms. So their J is in the hundreds. They may only have samples of about 5 or 10 individuals in each classroom. That's not a critical point. We'll get back to that later. But that allows you to actually take a bare-assed empiricist approach much more easily than what we typically have, which is samples in the thousands, potentially, but very few relative numbers. 27 is in BES, when we make the somewhat favorable assumption that these are really all exchangeable units, so that we should not have to separate structurally, say, Eastern Europe from Western Europe. So that's the issue we run into. And even if we stay below this, this limit of J, it can still happen that we get estimates that just don't make a lot of sense. And this is another thing I really think we should focus on is when you do these kinds of routines where identification issues are a possibility, always double check the estimates and see if they make sense. And I'll just show you, because I got to this point already before and I didn't really show you what problems can occur. But here is this Obama example that we dealt with before. So I now have the feeling thermometers as an independent variable, race of the respondent, percentage black in the state. There's no descriptive term interest interaction between those two things. Actually, then we have state. I let the effect of black vary. Covariance is unstructured. So let's see what happens when we estimate this. This is in theory identified, just to point out. So what are we estimating? We're estimating 1, 2, 3 fixed effects plus a constant, so we're 4 fixed effects. And we're estimating one error variance, so it's 5 parameters. And then critical, the level 2 error structure has 3 components. Variance of the intercept, variance of the slope, covariance between the intercept and the slope. 3 parameters with 33 states. That's plenty of degrees of freedom to do this. So it should work in theory. Something wet. Something went wrong already when I tried to create this data. Syntax. Everything is already defined. So this goes pretty quickly. And this is then the set of estimates that we get. So this is the variation in slope, 45. This is the variation in intercept, 43. This is the covariance between the slopes and the intercepts. Now that looks fine. But now I will re-express some of this as something that drives me nuts about Stata is that they're not consistent in how they let you do things. So now I re-express this variance-covariance matrix as a correlation matrix. So this is the correlation between the intercepts and the slopes. You want to look at this. It's actually, I was wrong. I said it was a positive one. It turns out to be a negative one. Makes more sense, the positive one. But this is still, this is a corner solution, as we call it. It's basically, it's pushing it. And it's a sure sign that there is an identification issue. When you get this kind of a mess occurring, don't trust. Even though it says that it converged and it was very happy and it did it very quickly, I don't believe this. That's why I then went back and said, let's just drop this, because I don't think this can be estimated. But you have to be very critical in terms of evaluating the output. So do this kind of thing, because this is actually still technically a proper variance and a correlation matrix, but it's almost not. And so I would basically state, and this is a command I use a lot, this P-stat covariance. I always forget what it's called, but I do it a lot. And I do this correlation option just to see what is going on. In this case, I then decided, okay, I don't think it's identified. In theory, it's identified. We have enough level 2 units in theory, but in practice it's not. And so this is the kind of thing you want to do. We want to go back and evaluate these things and be very critical about the outputs. Because it's not a rare event, I have to say, that it looks like it has converged and then it really hasn't. And we don't want to be the person who published a paper where a year later someone points out, well, but model was not identified. That's not the kind of attention we'd like to get. So this actually, what I did here is a very common thing that people do in estimating these models. In fact, here are a couple of identification strategies that I see a lot. The first one sort of drives me nuts, although it's incredibly common in political analysis. Just do random intercepts, then you never have a problem. But that is really problematic in the sense that one, it underutilizes a very powerful tool. And two, it actually can actually produce specification errors, where you're basically saying, well, if there is variation in the slopes, I have perfectly accounted for it with my predictors, my level 2 predictors. That's at least something you want. check. The other strategy that I see a lot is that people just don't estimate covariance components between slopes and intercepts. That's what I opted, but that's what I ended up.
What is that?
Do you have a problem for the time?
No.
So that's what I actually ended up doing here. Is I ended up re-estimating this instead of using the unstruck I set in depth, which means now you're forcing this covariance tau 0, 1 to be equal to 0. And this is what I see a lot. And it reduces the number of parameters dramatically, but it's not always clear that it is the right strategy. And one place where I am convinced it's not the right strategy is when you have categorical predictors. And I actually have reviewed papers that do this incorrectly. So, say the categorical predictor, we should have had in this model, which is partisanship. Say that this partisanship I dummy up. So I say, well, I don't really care about using the original 7-point scale in the AES. All I care about is Democrat, Independent, Republicans, so I create 2 dummies. Say one for Democrats, one for Republicans, and I use independents as the baseline category. And now, what people then do is say, okay, say that has a random effect. And then they say, okay, we have a variance component for Democrat dummy, a variance component for Republican dummy, and no covariance between their slopes. Well, given that these really are produced by one and the same predictor, I think that's a fairly heroic assumption. And I think you should not specify it that way. I think you should allow there to be a relationship between the effect, the variation in the effect of Democrat and the variation in the effect of Republican. So that's one place where I would say don't opt for this second identification strategy. Does it make sense what I just said? I mean, so you have these dummies, they come from one and the same variable. That's the critical piece here. There I would say don't allow the slopes, there I would say allow the slopes to covary. And unfortunately, I've gotten papers to review that don't do that. And I don't take kindly to that. So that's an issue. So these identification issues have to be taken seriously. What you always should do is figure out in theory is it identified, and then do these checks that I did before. Re-express the covariance matrix as a correlation matrix and see whether you get things that look reasonable. If they don't look reasonable, then probably they're not reasonable. I mean, it's in theory possible that it really is true that the slope and the intercepts correlate at -0.99, but it's very unlikely. In this case, I think we're also sort of running into one of the well-known problems, and I will get into that more today, that when we have 33 level 2 units, you can do multi-level analysis with that, but it's sort of pushing it. I mean, the recommendations on how many level 2 units are always a little bit hard to assess. Some people say 50 at least, and other people say 100 at least. Part of me says, well, it of course depends on how huge the cross-level variation is in terms of statistical power. If it's really enormous, you should be able to pick it up even with relatively few level 2 units. But there are some issues in this in estimation, and this actually gets me to the next topic, which I want to keep relatively non-technical. So, but I do have to talk a little bit about estimation, especially because there's sort of three things we're estimating, we're interested in potentially. One is the fixed effects, the other is the variance and covariance components, and then the third is actually these random effects, these betas that we talked about. And they're estimated there's sort of different strategies for estimating these. So the fixed effects are the least problematic part of the estimation. And they can be estimated in basically any number of ways. Least squares estimation is actually perfectly fine. That is to say, if you have this multi-level model that I've presented and you're only interested in the fixed effects, you can run that through an ordinary least squares. And if you have a correctly specified model, that is, you have the proper level 1, the proper level 2 predictors, and the proper cross-level interactions, the least squares estimators are unbiased. Now they have the wrong standard errors, but you can correct that. Either by running cluster correct standard errors or by following the strategy that is outlined by Lewis and Linzer. And that is, I think, a quite good strategy. This is a paper from Political Analysis. They had a special issue on multi-level models when they have large cluster sizes, and they lay out strategies for estimating the model there. What I just showed you, what Stata does is to use maximum likelihood, and that is the most common estimation procedure for reasons that will become apparent in a moment. Namely, that maximum likelihood is also a very good approach to estimating the variance of the covariance components. But is something that originally I had intended to do in this class, but then I got cold feet, is to teach this as a Bayesian class. But then I thought, well, you know, I'm going to be spending one day explaining Bayesian inference and then a morning to cover everything multi-level. That doesn't seem to make much sense. But Bayesian is actually a good way to go with these models for reasons that I will talk about later. There are several reasons to do it. So, as I said, the least squares estimation procedure should not be ignored, especially not when the cluster sizes are large and primary interest is in the fixed effects. And this Lewis and Linzer approach is very useful. What they do is they sort of do a two-step estimation. So they say, we have 27 countries in the EES. Let's estimate a model in each of these countries and get the betas. Those are then effectively the beta with the subscript J. And then, in a second step, explain them using level 2 predictors. And then you get your gammas. And then you have to adjust the standard errors, and they point out how to do that. And it's a fairly useful strategy. Wouldn't work if you have cluster sizes that are really small. We'll get to that point in a moment when I talk about empirical Bayes estimation. All right, that's all I want to say about the estimation of the fixed effects. What you should get away from here is that this is not the part that we worry about. This we can do in any number of ways that are all equivalent, are all unbiased, and that should give you headaches. Estimation of the variance components is a different story. Their least squares doesn't work, and what you want to do is either use maximum likelihood of Bayesian inference. There's also some special cases, especially with this random effects in NOVA, where some other estimators are available, but sort of the general purpose one, are maximum likelihood and Bayesian. And with maximum likelihood, because we will not talk about Bayesian, there are actually two choices that we have available. Something known as full information maximum likelihood and something known as restricted maximum. So, what a full information maximum likelihood procedure does is it estimates the variance components and the fixed effects in one step. And it estimates them simultaneously. And the way this is then done, just to give you a little bit of background, is to say, okay, what is the distribution of the y's? That ends up being a multivariate normal distribution. And then based on that multivariate normal distribution, you can derive a likelihood function. And the likelihood function is basically a function that gives you the likelihood of observing the data given the fixed effects and the variance and covariance components. So you think of it this way: if you would plug in values for these fixed effects and these covariance and variance components, then you would obtain a value for the likelihood of the data. And then the maximum likelihood estimates are those values for the fixed effects and the variance and covariance components that maximize the likelihood. And just to give you a bit of an intuition of really what this likelihood looks like. A very complex idea, but it is really not that complex. And one of my sort of failures in life, I guess, is that I wasn't like Sir Ronald Fisher, who figured this out when he was an undergraduate at Cambridge. I was doing very other things when I was an undergraduate, not figuring out fundamentals that are still used in statistics today. But imagine that I have observations drawn from a normal distribution, and there are these observations here. So this is, and then I tell you, well, there are two possible normal distributions that generated these. There's this normal distribution here, and there's that normal distribution here, and these are drawn based with a different value of the mean and the variance. So this is a low mean and a low variance. This is a high mean and a high variance. And I ask you, which of these two distributions is more likely to generate at these three data points? What would you say? The blue one or the red one? Who thinks it's blue? And who thinks it's red? The red is the right answer. And the reason is, if you sort of think about it, okay, what is this blue distribution? We're sort of in the tail here. What is the probability of observing values this extreme in the blue distribution? Very small probability. Here is a much higher probability with the red curve. And that's why we'd say, well, the data are more likely to be generated by the red normal distribution than by the blue one. And in maximum likelihood, you sort of take that idea, except you sort of put it on its head, because here I said, well, I know which curve, and I'm asking, okay, how likely is it to get the data? And normally, of course, you don't know the curve, we have the data. But you can use the same principle. You say, well, when given these data, which parameters, which mean, which variance is most likely to have produced the result of interest. And that's what we do here. And now it turns out in theory, this is an optimization problem. So you may recall, say you have a likelihood function and you want to find the maximum, so this is your likelihood function. Then you want to find this point where the slope of the tangent is 0. So what you would do in theory is take the first derivative of the likelihood function and set the derivative to 0. Turns out that you don't get very far trying to do that with these functions we're dealing with. These likelihood functions that we're dealing with are very complex. So what happens in the estimation is that we find the maximum through an optimizer, usually as the Newton-Raphson algorithm. So this optimizer is basically an intelligent way of trying out different values till we get to the maximum. And that's what you actually see when you look at the program as we have here. You see a bit of the history of that. So the optimizer works this way. So you start with some starting values, so your initial guesses of the fixed effects and variance components. The chances are that you haven't picked those so fortunately that you already have reached the maximum of the likelihood. So then you need to update it, and you see each of these steps is an update. It's called iteration, it's an update of the values. And what you'd like to see is that it doesn't take an awful long time to get to the final estimates. The final estimate is picked in such a way that they say, well, the change in the log likelihood, which is the natural logarithm of the likelihood, is so small, who cares about this thing? And then the algorithm stops. Let's here after 4 iterations. And we will see this number here, this negative 10,521.412 is a number that we will be using for hypothesis testing purposes later. But that's what the algorithm does. And there is a variation on this, and that variation is restricted maximum likelihood. And what does restricted maximum likelihood do? Well, it overcomes a little problem in maximum likelihood, which is if the number of level 2 units is relatively small, it turns out that the estimates of the variance components that full information maximum likelihood produces, those estimates are too low. They're downwardly biased. Restricted maximum likelihood corrects that. And one way to think about this is it adds a penalty term to the likelihood estimates, or to the likelihood for estimating the fixed effects. It's a bit like this. There are 2 ways to compute the variance in a sample. One way is to do this. Take the sum of the observed values minus the mean squared and divided by n. That turns out to be the maximum likelihood estimator when you have a normal distribution. But this is biased. In small samples, when n is small, this is a downward bias. So what we do instead is we calculate this thing. Almost the same. It's the sum of the squared deviations from the mean, but instead of dividing by n, we divide by n minus 1. And we say we lose a degree of freedom because we had to estimate this y-bar. That's what restricted maximum likelihood does, in a sense. It's correcting by subtracting the degrees of freedom that we lose by estimating fixed effects. And it turns out that by doing that, you end up removing the downward bias. Now, even though that's true, I hardly ever use restricted maximum likelihood myself, because too many things can go wrong, especially when you compare models. You have to be extremely careful that you keep certain things constant. We'll talk about that when we discuss hypothesis testing. Now we come to the piece that's probably the most exotic, and that is the estimation of the random effects, the betas that we talked about earlier. And these are actually, even though we don't use a fully Bayesian approach, it turns out they are actually Bayesian estimates of sorts. Now, let me just briefly digress. And if this gets too far, you can live without it, and you can understand the rest without it too. But Bayesian inference is different from the way we usually do things, because what we end up saying is, well, we have maybe prior knowledge about parameters. And this prior knowledge about the parameters we can encapsulate in the prior distribution. And then, so that's before we've looked at the data, we have some prior expectations about the parameters. Maybe because we've already done a similar study several years earlier. Or maybe the literature suggests a certain effect of a predictor, and we can say, well, then we bring that in prior. And then we look at the data. And that, looking at the data, is captured by the likelihood function. That provides new information about the parameter of interest. Now we combine these two pieces. The prior and the likelihood get combined into a posterior. And this posterior distribution is what informs us then about the estimate. So this posterior distribution is not just a function of the data, because it also has some prior ideas going in there. And so it could, in theory, be the case that if the data are weak, that most of the emphasis goes on prior. If the data are very strong, most of the emphasis goes on data. And this combination of prior and likelihood, that is called, is Bayesian in the sense that the posterior is based on Bayes' theorem. Now, that's what we're working with here as well. So we have a posterior distribution of these betas that we can come up with, but it's a different kind of posterior distribution than what you typically find in your Bayesian setup. Because in the Bayesian setup we say, I know everything about this prior. I can tell it what variance it had, I can tell it what means it has. And here we say, actually, the only thing we assume about the prior is that it's normally distributed, because the deltas are assumed to be normally distributed. And the rest of that prior is informed by the maximum likelihood estimates that we've already obtained of the fixed effects and of the variance components. So that's what is empirical about it. It's sort of like, in a strict Bayesian world, the posterior is formulated before you ever look at the data. In this empirical Bayes world, you create the posterior after you've looked at the data, because you're using information from the data. But nevertheless, you can get this sort of posterior that you can then use to say something about these random effects. Now, what effectively actually happens is that these empirical based estimates that you get out of this posterior are a compromise between two different estimates. And to go back to this example that I had before, what they actually end up doing is they end up saying, well, we have an estimate of the grand mean that informs us about the groups, and we have estimates of the group means that inform us about the groups. Let's just combine the two. And not just combine them in the sense of let's average them out, because that doesn't seem right. What we do is we average them, but we use a weighted average. Because we're going to give the biggest weight on whichever of these is more precise. That's the idea. Now, this is a bit of a technical discussion of that idea, but it gives you a sense of what happens. I mean, to depict this in general terms, like for a general hierarchical linear model, it gets very complicated and it would require me to delve into matrices, and we don't want to do that. So I'm doing it for simple model. This random effects ANOVA. We already saw this before. And now the question is, well, what are the estimates of these beta 0j's that we actually can come up with? Well, the second equation suggests already one estimator, and that's the estimator of this gamma 0, because the idea here is that these beta 0j's are draws from a distribution with this common grand mean gamma 0. So that gamma 0, as this equation implies, provides information about the individual betas. That's one way to do it. The other way to do it is to say, let's just calculate the mean in each of these groups and use that as an estimate of this beta 0j. So one estimator is to calculate the group mean in each group. That's what this means here. This y bar dot j is the group mean in group J. And this gamma hat 0, which is the grand mean, is equal to y bar dot dot. The dot here indicates that you're averaging here over both individuals and groups. Here you just average all the individuals in a particular group. So now we want to combine these two estimators. Well, how will we do that? We take their precision into account. And the precision of the grand mean is given by tau 0, which basically tells us how much the group means differ from each other. Because imagine that tau 0 is 0. That means these groups have all exactly the same mean. Well, then this grand mean is very informative, because it's exactly the same as each group mean. Imagine though that we have huge variance across these groups, then you don't want to use the grand mean to tell what the group mean is, because the deviations from that can be huge. The precision of the group mean is given by the standard error of the variance of the mean, which is sigma squared over nj. And that's the usual formula for the variance of the mean. Now what we're going to do is to use the following weighted average. We create a reliability lambda j that is equal to tau 0 over tau 0 plus sigma squared over nj. And that is the weight we give to the group mean. And then 1 minus that is the weight we give to the grand mean. Now why does that make sense? Imagine the following. Imagine that there is no variation in each group. Sigma squared is 0. Everyone in a particular group has exactly the same value. Then what that would mean is that the group mean is a very good predictor of an individual. Because everyone in that group effectively would have that value that we calculate to be a mean. So all of the way would go to the group mean. On the other hand, if there is no parameter variance, that is tau 0, 0 is 0, so these group means are all the same, then you want to give all of the way to the grad mean, because that is then effectively based on more data anyways and is just as informative as looking at the group means. So that's what I have here. The first limiting case is sigma square is 0, then the empirical base estimator is just a group mean. The second case, tau 0, 0 is 0, then the empirical base estimator is just the grad mean. Now, there's some other terms under which this thing goes. It's the mean of the posterior distribution. It's also known as the best linear unbiased predictor. It's also known as a shrinkage estimator because it shrinks in the direction of the most reliable estimator. And this shrinkage principle is sometimes touted as a major benefit of multi-level analysis because it allows for interval strength. And this gets me now to something that is quite different from the scenario I discussed earlier. Earlier I said, okay, sometimes we have enormous cluster sizes. Now let's imagine the opposite scenario where we actually have very small cluster sizes. And that can happen because if you sort of, for example, look at how many observations come from the different states that I have in my example, you'll see that that varies quite wildly. So I'll just give you a flavor. The first state here is Alabama. We have 22 observations. Arizona, we have 40. And then you sort of go down through the various states. And you see some of them is quite high, some of them is quite small. In fact, you can get a pretty good indication of this when you look at the top of the data output. Here it tells you the number of level 2 units, the number of level 1 units, and here it tells you something about the range of the n sub j. So in California, I think this is California, we have 362 individuals. And then we have 20 individuals in another case. And on average, we have slightly less than 70 observations per state. In an example we will get to later today, where I look at British election study data and the various constituencies, you will find that sometimes things get even smaller than that. And now we get to a situation where this strategy that Lewis and Lindsay described may just not work, which is run the regression in each group and then in the next step do something with the regression estimates. Because if you have 5 observations in a particular level 2 unit, then you cannot really reliably estimate a regression. It may even be impossible to estimate a regression when you have more parameters that you want to estimate, more fixed effects than you have observations. So herein comes then this borrowing strength. This idea that is then touted to be one of the big benefits of doing this kind of work. The idea is that sometimes with in-group estimation, so running a regression in a particular state or a particular constituency, is impossible because the number of cases in that unit is too small. But because we can borrow strength through this empirical base estimator, we can actually still calculate an empirical base estimate. Because what will happen in such a unit where we could say only very imprecisely estimate the effect of a predictor is that in that unit more weight is being placed on the fixed effects estimator. And that means that that estimator is based on all of the observations. That's where the idea of borrowing strength comes from. This gamma that we estimate is based on everything we have in the data. So California can help out the estimation in Alaska. Alaska is not in the sample, but I assume it would not have many cases if it didn't work. That's sort of the idea. So that's useful where the NJ is small. It's not always a problem in electoral research, but it can be a problem. Like this data that I will use this afternoon on British elections has that problem. So what we have then is a strategy to compute these random effects and then also interpret them. And what is nice is we can compute these random effects even if within group regressions we fail or would be horribly imprecise. That's what we end up getting out of this. And this then brings me to sort of a point about the asymptotics. Sort of how many cases. And I've mentioned this before. The problem is that we don't really need such big cluster sizes, precisely because we have this borrowing strength idea going. So I've seen cases where people may have 4 or 5 observations in a level 2 unit. That's not such a big deal. What is a bigger deal is having enough level 2 units. And that again goes back to the ability to really estimate the variance components effectively. And that is a more important thing. So the asymptotics in J are actually more important in a sense than the asymptotics in N, to put it that way. Now, that said, you may want to think a little bit if you have, say, really insufficient numbers of observations to really do a within regression. Say you have 2 predictors and an intercept for which you want to compute effects and you only have 2 observations in a particular level 2 units, then you couldn't do the regression physically. Then, of course, the empirical base estimate is going to be solely based on the fixed effect. And there you might want to say, okay, maybe those cases you want to think about, whether you should include them or not. I mean, technically there is no reason not to include them, but you sort of start thinking, okay, what do they actually contribute? So that's a question that you want to think.
I mean, this is not the country sort of example, but what happens if your sample size, so NJ, is basically related to the nature of which cluster you are in. So you have a small sample size in one group exactly because of some characteristics of that group. Now how would that, so if it's not the country, the classic second level where, let's say you don't choose necessarily where you go, I mean in states maybe, but again something like a school or some people run models with parties as nesting levels. And then this would mean actually that in a way the sample size is correlated with some sort of characteristics of the nestation unit on the second level, whether that, in that case the sample size would be a problem. So borrowing power from Los Angeles to a different state is okay, but borrowing power from a center conservative whatever party with many supporters, estimate the effect for an extreme left party that has only 4 cases. I don't know whether that is a problem or this sort of argument holds.
I'll give you the simple answer is no. And the more complex answer is, well, it might be, because what you start to worry about in the scenario that you described is actually some other specification issues. So this NJ being a function of the cluster might also then actually say something about, well, maybe these clusters are not exchangeable, or maybe different dynamics operate for these states, or perhaps you might even have a situation where you end up having selection biases that you really need to model out in order to get valid inferences. I mean, you could also imagine, for example, this is a similar situation when you think about, okay, individuals nested in parties, and you talk about parties that sort of, say in a particular country, have a semi-illegal status. That individuals would be very reluctant to admit being members of those parties or adherents of those parties, then being missing as a result. So you get this small cluster size, but in this case is an indication not of the fact that there are not that many individuals there, because that wouldn't necessarily be a problem, but more a situation that, well, you're having tons of missings because of some selection bias that is going on, that you would have to really take into account, or else you're getting invalid inferences. So the simple answer is it doesn't have to be a problem. Because I mean, I could say, well, I want to include Liechtenstein in my sample, and I want to, in principle, have 1 million Liechtensteiners to study, and they just don't exist. I think they don't exist. I don't think Liechtenstein has 1 million people. That is not so much a problem. More a problem if you get sort of these relationships between clusters and cluster sizes because of weird selection biases, then you would really worry about it. Because then either you have a fundamental problem with selection bias, or you have some issue where exchangeability might be questionable.
The small green part, they're like 6% probabilistically if your sample is good. You will not find that many.
Yeah, that's true. I mean, that's absolutely true. So, well, there's another kind of approach there. I mean, ideally, you would sort of adjust your sampling design maybe to capture these people. But short of that, you could, of course, also weight data to weight it up to the empirical presence of these individuals. And that's what people then tend to do. That is actually, with these small parties, there's a big issue. You usually lose small parties because you end up with 5 people who say they voted for it. And then it's better. The waiting would be a solution in that case. Are there other questions? So the bottom line is, at least what I end up doing, but that's because I'm not a big fan of these restricted maximum likelihood things, is that I estimate these things using full information maximum likelihood, and then use the empirical based estimates to say something about the random effects. And well, that would be my strategy to estimate these things. But there are some alternatives. Again, if you have large cluster sizes and you're just interested in fixed effects, you may just want to do these things. At least it's not wrong to do it. In fact, that was till the mid-1980s, that is sort of how people estimated these models, because the algorithms to do maximum likelihood estimation simply were not there yet. They all sort of came around 1985, 1986, 1987. So that's when there was a big bump in papers talking about maximum likelihood. Now, one last thing about empirical base, because Stata, in its infinite wisdom in this XT mixed business, doesn't actually give us the empirical base estimates, but it gives us empirical base residuals. And what are these things? It's basically the difference between beta 0j and the fixed effect. So actually, to turn these things into empirical base estimates of the effects, you just simply add the fixed effects estimated. That will be the trick. And to get these empirical base estimates, this is the syntax. Predict B, this asterisk is just a placeholder. So Stata can say B1, B2, B3, B4. Refects is random effects, and level tells Stata at which level do you want these random effects. If you would specify the individual here, what Stata would do is add its estimates of the epsilons, and then you get that. But that's usually not what we're interested in. What we're interested in is the estimates of the deltas being added to the fixed effects, and that's what you do by specifying the level 2 unit where it asks for level. So all of this is the technical stuff. Then comes actually what is really, I think, the most important part in the interpretation. And I have some strong preferences about interpretation, and they don't seem to agree with what is usually done in the literature. What usually is done in political science when people report multi-level models is they focus just on fixed effects estimates. I think that's sort of a waste. Why do all this stuff that allows you to get good estimates of the random effects and then not bother to interpret the random effects? So I actually, myself, am inclined to really do more with these random effects. But that said, I'll start with discussing the interpretation of fixed effects. And the nature of the interpretation of the fixed effects is to basically average over level 1 and level 2 units so that all the error components disappear and the only thing that you have left is the fixed effects. So we already saw this model. Outcome, intercept, effect of the level 2 predictor, effect of the level 1 predictor, cross-level interaction, error term. And what is done is to say, well, let's average this over individuals and over states in this case, so that delta 0j, delta 1j, and epsilon ij can all be assumed to be 0. And what we're left with is a prediction of the mean of y that is equal to gamma 0, 0 plus gamma 0, 1 zj plus gamma 1, 0 xij plus gamma 1, 1 zj times xij. This is by far the most common mode of interpretation that I see. Now, it's a fairly straightforward kind of interpretation. What I would like to do is first sort of ignore that we have a cross-level interaction and then focus on this cross-level interaction specifically. So imagine that this gamma 1, 1 equals 0, so that what we really have is just this equation here. The mean of y is equal to gamma 0, 0 plus gamma 0, 1 zj plus gamma 1, 0 xij. Then the interpretation is just like any regression model. Gamma 0, 1 gives the expected change in y for a unit change in z. Gamma 1, 0 gives the expected change in y for a unit change in x. That's all there is to it. No more complicated than that. So just like you would interpret any other regression model. But with cross-level interactions, it gets a little bit more complicated. Although if you've ever done interactions in a normal regression setup, you will recognize that this is essentially the same thing. So what we have is a method of interpretation that is based on something known as the simple slope equation. There's a detailed discussion of all of this in the paper by Bauer and Karen, but the basics are over the next couple of slides. The simple slope is a conditional slope, that is to say it's the effect of one predictor given another predictor. And here is what it is for the effect of x given the level 2 predictor z. And simply the derivative of this expression here with respect to x, and that leaves you with gamma 1, 0 plus gamma 1, 1 zj, where z now serves as what is known as the moderator, the thing that influences the effect of x on y. Now you can also, of course, say, well, what is the effect of z given x? And that would just basically be the same thing, but now you differentiate the mean with respect to z, and you get an equation gamma 0, 1 plus gamma 1, 1 x ij. I like this method of interpretation because it lends itself to very easy graphing, and it's actually, when you read the political analysis piece by Bramber et al., it's basically that approach applied to multi-level models. Now, the only thing that I also like to do is to include confidence bands around these simple slopes, and to do that you would have to know the variance of these random effect, or these simple slopes, rather. But you can get that pretty easily by applying these equations here. So for the simple slope of x given z, it's the variance of the effect associated with x plus 2 times the value of z times the covariance between the effect associated with x and the interaction, plus z squared times the variance associated with the interaction. And asymptotically, at least, that thing is normally distributed, and so we can use a normal distribution to create this confidence intervals. So earlier we estimated this model of the Obama ratings with a cross-level interaction between the race and the respondent and percent black. And to go back to these estimates, it's been a while. It was this one here. We have now, I want to do the simple slope of black given percentage black. What we have is the effect of black is 14.10 and the interaction is 0.96. So the simple slope equation for the effect of black is going to be 14.10 plus 0.96 times percentage black. That's what we're going to take advantage of in the interpretation. And the simple slope then is this equation, and to get to the variance, well, I did that in a sort of dumb way here, so there is a more intelligent way of doing it. But this is the set of results that you get. Variance for the effect of black is 7.96, the variance for the interaction is 0.02, the covariance is 8.37, and then if you look at the simple slope, then you see that indeed you get a positive relationship, which means the gap between black and white increases as the percentage of black increases. And this is the confidence band that I've drawn around that. Now, let me show you a little bit of how you get the pieces that I used here to construct all of this. And I first, I think, have to go back to re-estimating this model here. Because I want to estimate the way I did. And so what I did is just redo this but specifying independence. So now we have this model here. There's a couple of ways to get these estimates of the variance. One way is to type E stat VCE. And this gives you the variance covariance matrix of the estimators. And this is the this portion you can ignore for what we're doing because that's the variance covariance of the estimates of the various components. And this portion is the more critical portion because that's the variance covariance matrix of the estimates of the fixed effects. this portion here in the bottom quadrant would be the covariances between the estimates of the fixed effects and the variance and covariance components, but you see they're all 0. That's a particular feature of the distributional assumption that we've made. We've made an assumption that the y's follow a multivariate normal distribution. In a multivariate normal distribution, the variances and the means are unrelated. And this is essentially talking about the means, this is essentially talking about the variances and covariances, and this just captures the fact that they're independently estimated. So, for our purposes, what we would need is the variance of this estimate of gamma 1, 0, that's the coefficient associated with black, that's this here. We would need the variance associated with the interaction, that's this piece here. And we need the covariance between the black and the interaction, that's this piece here. And then we can construct the confidence interval. Now there's actually another way to do this that requires way less work on your part. If you're particularly interested in one value of the percentage of black and then want to find out what the simple slope is, you can do that in Stata with a so-called lincom command. Lincom stands for linear combination. So say I'm interested in a case where the percentage of blacks are in the state are 30, then I could do lincom black plus 30 times inter, that should be black. And then what Stata will report here is the estimate of the simple slope when Z, in this case, the percentage of blacks, is 30. So this is the expected gap between black and white respondents in the evaluations of Obama. And this is the confidence interval, the 95% confidence interval that gets created. That's a little bit easier. If you want to graph things like I did before, it's easier to work to actually write out the formula for the variance and deal with it that way. But this actually can be used as well. And I think in general it's good to have pictures like this when you present your results, because they say a lot about what's going on in the model. And it's immediately clear, especially if you perhaps use labels and titles on the axes that are a little bit more self-explanatory, that what you see is that as the percentage of black in the state increases, the gap between blacks and whites increases as well in terms of evaluations of Barack Obama. Also, at no point is a 0 included in the confidence interval. So at no point can you say, is the difference between whites and blacks insignificant? Even when the percentage of blacks is really fairly minimal, there's still a gap between blacks and whites, but it's a gap of only about 15, 16 points, whereas here, this is Mississippi, 37% black. That gap is more in the vicinity of 49 points on a 100-point feeling thermometer. So this is a pretty sizable effect. Now, I wouldn't stake my life on this, given that the rest of this model is hopelessly misspecified. There's no party in it, there's nothing else in it, but I mean, this is what I would like to see as a reviewer. I like pictures. Because my eyes are so terrible and I like to read text so much, but pictures are helpful. Now, you could also reverse this, and you could say, well, what is the effect of percentage black on the average evaluation of Obama, and do that for whites and for blacks, and then you say, then we end up getting this equation, negative 0.73 plus 0.96 times now x, and for whites, x is equal to 0, so you get negative 0.73, which suggests that for white individuals, as the percentage of blacks in the state goes up, they become more and more negative towards Obama. And for blacks, you get a 0.23, which is not quite significant, but suggests that there's a slight tendency for blacks to become more favorable as the percentage of blacks in the state increases. You can see this here with the confidence intervals. You see a pretty sizable, significant effect for white. For black, 0 is included in the 95% confidence interval. So the effect of black doesn't seem to be affected. Black people don't seem to be affected so much by the percentage of blacks, but white people certainly seem. And that's then, of course, also, again, telling us that the gap between blacks and whites increases when the percentage of blacks in the state increases. Now this is, well, not even this is what people often report in these papers, but this is one thing I think you should do. When you have cross-level interaction, if you don't have a cross-level interaction, then you basically can say, okay, here is, for a unit change, this is the effect of my P predictor. Don't do it for every predictor because it gets terribly repetitious to read that sentence. But basically say, well, this is my core predictor and here's what happens. But with a cross-level interaction, I think it helps to have pictures like this, or picture is not that helpful when you only have two categories of the moderator and the table that I tell you the story to. Here's what I think people should do more of. But before I go there, what's the time?
1.
Then we're not going there. I want to talk about random effects next, but we can do that after lunch.